Hello, everyone. Welcome back to the Algebraic Graph Theory seminar. Today we have the first seminar in this year. And it is my pleasure to introduce Alexander van Werde, whose talk will be towards generalized spectral determinacy of random graphs. So take it away.
Yep. So thank you for the introduction. And let me also thank the organizers for the opportunity to speak here. So indeed, my name's Alexander, and I'm a PhD candidate in Eindhoven. Now, I will note that my research is actually mostly in stochastic processes and random matrix theory, which are topics in probability theory. So it may be reasonable to wonder what I'm doing at the algebraic graph theory seminar. Well, in some recent research, it's what my talk will be about, I used some tools from random matrix theory to study a problem from spectral graph theory relating to the spectral characterization of graphs. And that's what I'm going to speak about. Before I start, let me also note that I very much welcome questions, so feel free to interrupt me during the talk. I think I have plenty of time, so I'd rather have you stop me that I can explain than that you're lost, and well, there we are. So as I said, I will be speaking about the spectral characterization of graphs, which is a topic I think many people in this audience are familiar with, but I nonetheless want to start with some historical background. Now, spectral graph theory is the discipline studying what properties of a graph can be deduced from the spectrum. So one starts with some network, composes a matrix, and then computes the spectrum, just to say the eigenvalues. And then often you can learn quite a bit about the graph on the basis of the eigenvalues. So for instance, say the chromatic number admits very nice bounds in terms of the spectrum of the adjacency matrix. Now, spectral characterization regards the question whether how powerful exactly this approach is. So for instance, one may wonder whether it's possible to recover complete information about a graph on the basis of the spectrum. Would be quite great if that was always possible, but actually, sadly, it is not always possible. It is well known that there are, in fact, non-isomorphic graphs which have the same adjacency spectrum. And it's not hard to find these, so I think the smallest example is already on 5 nodes. So you can find these by hand. Not only do such graphs exist, in fact, this situation is typical for trees. Almost every tree admits a cospectral tree, which is non-isomorphic. This is a striking result from Schwenk from the 1970s. But of course, one may note that trees are only a very small proportion of all graphs. So ever since the striking result, people have been wondering what might be true in the general case. Now, this turns out to be quite a difficult problem. And actually, for quite a long time, people were not entirely sure in what direction one should be trying to work. That is to say, should one try to prove that the same as in Schwenk's results holds for generic graphs? Or should one be trying to show the opposite, that graphs are in fact often determined by the spectrum? Well, that was an open question, and in fact, this remains an open question. However, it is nowadays believed, at least by some, including me, that the opposite from Schwenk's result will happen. So there is numerical evidence, for instance, supporting that almost all graphs will in fact be determined uniquely by, say, the adjacency spectrum. However, as I said, this is still an open problem. And one of the reasons for that is that we have very few proof techniques for the positive direction. So if I give you a graph, it is not necessarily very difficult to show that it's not determined by its spectrum, if that happens to be the case, because you can simply construct a cospectral graph. If I give you an example, well, there we are. And in fact, there's quite a few proof techniques which can be used to do that. So if I give you a graph, there's a set of tools which you can use to try to prove that it is not determined by the spectrum. So for instance, Schwenk's result also came with one such method. In the opposite direction, however, we do not have many techniques. So if I give you a graph and it happens to be determined by its spectrum, that's going to be a lot more difficult to prove in general. To give some idea about this, I may note that for the adjacency spectrum, the best result is due to Koval and Kwan, who established that there's exponentially many graphs determined by the spectrum, which is a recent result and was in some sense a breakthrough because previously the bound had been stuck at exponential of square root n. However, one should note that exponentially many graphs is in some sense not that many, considering that there's exponential of n squared many non-isomorphic graphs on n vertices. So the fraction shown to be determined by spectrum, by Koval and Kwan, is still very small. And they suggest that the proof techniques which are currently available are in fact also just not going to be sufficient to go much further than this. Because the only proof techniques which we have, which is also what they used, is to study very specific classes of graphs. And then the main contribution in their results was also to find some sufficiently large but well-behaved class of graphs where one can do something in the positive direction. For generic graphs, however, things stay difficult. All right. So just using the adjacency spectrum, things appear to be rather difficult in the positive direction. And it was proposed back in the 1980s by Johnson and Newman that all these difficulties might in fact be a symptom of some deeper issue. They proposed that instead of looking at the adjacency matrix, which has arbitrarily chosen to have entries 0 and 1, we should somehow consider these entries, 0 and 1, to be more formal symbols. Okay, that was their proposal. And they then also proposed a notion of cospectrality corresponding to this generalization. So we'll say that the two graphs are generalized cospectral if the generalized adjacency matrices have the same spectrum for every choice of the parameters. And here, by the generalized adjacency matrix, I mean that we start with the usual adjacency matrix, but now we replace 1 by some symbol x and 0 by some other symbol, say y. And then if for every choice of x and y, these spectra are equal, then we're happy. Then in fact, these graphs are considered to be generalized cospectral. All right. And now, of course, one would actually be happy if this is not the case. So what we want is that many graphs are not generalized cospectral or uniquely determined by their generalized spectrum. Well, back in the days of Johnson and Newman, they could show that this is in some sense a well-behaved notion. So one could prove that it's equivalent to a bunch of other notions. But I would say it was not that obvious back then that this was really a solution to the problems which usual spectral determinacy has. More recently, however, there has been some very promising progress. In particular, Wang, together with some co-authors, found sufficient conditions for this notion of generalized spectral determinacy. So if I give you a graph, then you can use these sufficient conditions and possibly be able to prove that it is in fact determined by its generalized spectrum. So this solved one of the huge problems with the classical notion. And moreover, it has been conjectured, supported by numerical evidence, that these conditions are satisfied with non-vanishing probability. So if you recall what the situation was with the state of the art on just classical spectral determinacy, this would be quite significant progress. However, this also remains a conjecture. And Here also, it was not necessarily that clear what proof techniques one can use to make progress towards this conjecture. Now, this is what I will focus on in my talk. So I'm not going to resolve the conjecture necessarily, but I do want to develop some proof techniques which can be used to at least study this conjecture and hopefully in some future point in time actually resolve it. All right. So the first thing I will do next is to formally state what these sufficient conditions are, and then I will proceed to my new proof techniques to study it. All right. So the sufficient condition is going to be stated in terms of a walk matrix, which is a matrix associated to the graph. I will define this in a somewhat more general setting because I will need the generality later in my talk. So for me, I will just consider an integer matrix X, but in the concrete applications, one will want to take this to be the adjacency matrix. All right. And then the associated walk matrix is going to be the matrix, which has as columns, first the all ones vector, then X applied to the all ones vector, then you apply X another time, and so on. Now, the name walk matrix is because if one interprets X as, well, say, adjacency matrix, or perhaps counting edge multiplicities, then Wij counts the number of walks of length j-1 ending in vertex I. So for instance, if one takes this directed graph here, and one uses conventions like I said here, then for instance in vertex 5, there's 3 walks of length 2, and hence W53 is equal to 3. So this matrix has some combinatorial interpretation, which explains the name, but will not necessarily need that specific interpretation in my talk. All right. What is going to matter is that given this matrix, we can compute some properties which give us the sufficient condition. In Wang's original papers, this was using the determinant, but more recent papers have been emphasizing, and this was already in his proofs to some extent, that one should really be looking at the Smith normal form of this matrix, which they considered to be a type of numerical data in the recent literature. However, I will emphasize a slightly different perspective, equivalent though, that the Smith normal form is for me group theoretic data. So more precisely, let us look at the image of W. So the collection of all vectors, which you can realize by applying W to an integer vector, and define the cokernel to be the quotient which measures to what extent W fails to be surjective. Now, the Smith normal form, as I mentioned earlier, is equivalent to the group theoretic structure of this cokernel. So it is a quotient group of Zn, and depending on its structure, one will be able to say nice things. Let me also introduce some additional notation, just for simplicity. So if I have an abelian group, like the cokernel, and some prime power, then for brevity, I will denote G subscript PM to be the associated quotient. All right. Now, the theorem due to Wang, equivalently restated, is as follows. If we're given a simple graph, and we take X to be the adjacency matrix, then if the cokernel, or these quotients of the cokernel for different primes, have a specific form, then the graph is in fact determined by its generalized spectrum. Now, the specific statements here will not necessarily matter for my talk. What will matter for the current talk is that ultimately we need to care about these quotients of the cokernel. So in particular, you take some prime raised to the power 2. And if those are sufficiently well behaved, then one can in fact state that the graph is determined by its generalized spectrum. Let me also emphasize that in Wang's result, this is for simple graphs, so undirected and without self-loops. I will later in my talk be focusing on directed graphs, and that's for technical reasons of my proof techniques, which I hope to overcome in the future. But what I do want to emphasize here is that Wang's criterion is only for simple graphs. So there will be some spacing between my results and this result. All right. So if you recall, the conjecture which I'm interested in is that this criterion holds with non-vanishing probability, or for many graphs. As I stated at the start, I am a probabilist. And I do some random matrix theory. So that's also the perspective which I'm going to take. In particular, I'm going to think about X as being random. For instance, you may want to think about the adjacency matrix of a random graph. And I will then want to study how this cokernel is going to behave. Now, the cokernel is then going to be a random group. And so the question is, what does the distribution of this random group behave like? That's going to be what I will discuss in my talk. Let me maybe already pause to ask if everything is clear so far. Okay, so no questions so far. So this is then what I'm going to discuss. As I mentioned earlier, I will be taking the case of directed graphs. So the definition which I gave for the walk matrix also made sense in that case. And this is because it's going to make something easier. In particular, if I take a distribution over directed graphs, then I can assume that this matrix X, which I started with, that has independent entries. And that's probabilistically a very convenient assumption. However, it is to some extent a limitation of what I'm going to present, because what actually matters for the criterion is the case of simple graphs. And there you cannot simply assume independence because one has a symmetry constraint. And this does to some extent actually matter, although I am hopeful that I will still be able to remove this in future work. All right. Now, for my first result, I will make an additional simplifying assumption, but my next result is going to relax that to some extent. In particular, in my first result, I will assume that not only are the entries independent, but I will also take them to be uniformly distributed on some sufficiently large sets. So if you want to think about this graph theoretically, then this means that I start with a complete directed graph, including self-loops, and then for every directed edge, I just assign some random weights. And then X is the matrix which encodes this information. All right. Now, in the setting, which is of course very nice because I made some strong assumptions, we can give a very nice result, or we can very explicitly describe what the cokernel is going to behave like. In particular, recall that we care about this quotient of the cokernel modulo p to the m. Now, this is an abelian group, and since we have quotiented by p to the m, it's always going to have the following shape. It will be a direct sum of z mod p to the lambda z, where these lambdas are at most m. And the question of interest here is only how many such summands are there and what power is here. That is the possibly random structure which can exist. All right. Additionally, I will just assume that these lambdas are arranged in non-decreasing order. And I will also, just for notational convenience, add a lambda 0. This does not actually occur in this direct sum, but it makes the next definition a bit simpler. All right. Now, to present the right-hand side, let me define the delta J to be the differences between the subsequent lambdas. So the deltas are going to measure how much we increase. And just to present, simplify the formula, I start at the end. So I work from the end backwards. All right. And then I naught is going to be the number of lambda I, which attain the maximal value m, which in some sense, going to be a special case in the proof, although I'm not going to go into too much detail about that. Okay, well, given this data, the right-hand side here gives us an explicit formula for the limiting probability that the co-kernel attains that specific shape. And this right-hand side involves some infinite products, in the limit at least, which starts at I naught. And we also have some finite product, which particularly depends on these deltas, measuring the differences between the subsequent lambdas. Okay, so that's the statement of this result. What matters is not necessarily the specific shape of it, but what really matters is that it's explicit and that we can prove it, of course. So, okay, the next thing I want to show you is how we prove it. And in this specific setting, with this strong assumptions, the proof is actually quite simple. Because recall that the walk matrix is found by just starting with L1's vector, then applying x another time, and so on. These are the columns of the walk matrix. Now, what the proof involves is simply looking at this process. And recalling that X has independent and uniformly distributed entries, its action on the L1's vector is essentially going to be just a uniform random action, at least modulo p to the m. So the first vector in the sequence is just a uniform random vector. And then conditional on that vector, I still have quite a lot of randomness left in my X. So it's basically going to act, again, uniformly at random, and so on. So in some sense, you can just track this process. There is, however, one delicate point, namely, the subsequent vectors here are not independent. Because, for instance, it can occur with non-zero probability that the first vector here happens to be 0. But then, of course, all the subsequent vectors also have to be 0. Because acting by x on 0 remains 0. And more generally, if, say, x to the j applied to E is in the span of the previous vectors up to some power of p times some vector, then the same will hold for the next step. However, it turns out that this is in some sense the only obstruction to independence. So aside from this, one does have independence in these subsequent vectors, and using that and thinking about what this means for the co-kernel specifically, one can in fact derive that formula which I showed before. And I may note here that actually the specific shape of this obstruction is also very convenient, because the co-kernel measures to some extent how much the map W fails to be surjective. And that is in some sense related to whether the span is going to be the full space. So these powers pk here, these essentially correspond to the lambdas, the maximal pk which you can do. All right. So that is the global proof ID. I'm not going to go into too much detail. But what I want to emphasize is that, relatively speaking, this is quite an interpretable proof. Just analyze the definition of the walk matrix using these strong assumptions. But the technique is not very robust, because I need these very strong assumptions on the distribution. I mean, I heavily rely on this to say, for instance, that you only have that one obstruction which I mentioned, or that it acts uniformly at random. All these things rely fairly heavily on that assumption that it has independent and uniformly distributed entries. So this, in some sense, is also an abstraction if you want to go further, which I ultimately want to do, to the case of simple graphs. There's then two abstractions. One is the symmetry, which I mentioned I'm not going to solve in this talk. And the other is that you have a weighted graph here. We actually want to deal with unweighted graphs. So my second main result will concern the extension to unweighted graphs. And what will be of particular interest is that the proof technique involved is a lot more robust. All right. So for the second result, I will consider the case of unweighted graphs. And I will also present a somewhat simplified version of my main results. So actually, the theorem is a bit more general than what I will present, but the full formulation is also quite a bit more technical. So, if you're interested in that, I refer you to the paper. All right. So as before, I will assume that my matrix X has independent entries, but now they will not be uniformly distributed. Rather, they will be 0, 1 valued, just to say that we're working with a directed but unweighted graph. Additionally, because my results or my proof techniques are going to be a lot more robust, I can here also consider a somewhat sparser setting. So specifically, I will assume that we can be quite sparse. So we can go up to logarithmic, well, diverging relative to logarithmic average degree. Okay. Now, in the setting, oh yes, just because I'm working with a simplified version of my results, I'm going to need an additional technical condition. This is actually not needed for the main theorem, which I present in the paper, but this technical condition will simplify the statement of the results. One shouldn't worry too much about it. It's probably true. I mean, in this model, I think the condition actually is simply holds, but I have not proven this so far. So specifically, this technical condition for completeness is a type of tightness condition, saying that this co-kernel should stay of, say, constant size typically. So if I take a large constant, then with high probability, the co-kernel is going to be at most of that size. So it's just saying that it's not exploding as n tends to infinity. All right. Now, given this setting and this additional technical condition, I have proved the following. First of all, for every fixed prime, the same limiting law as I presented earlier still holds. And further, if you have some finite collection of primes, then the co-kernels living above those primes, so the quotients, are going to be asymptotically independent. So if I tell you what a co-kernel modulo 3 looks like, this is not going to tell you anything about a co-kernel modulo 5, at least asymptotically. All right, so that is the result. And I think this asymptotic independence is also somewhat relevant in the context of this sufficient condition by Wang, because there one also wants to understand, all primes simultaneously. So understanding the joint structure is not irrelevant. All right. Now, as I mentioned, what is really interesting here is that the proof technique is going to be a lot more robust. And specifically, I will rely on something that is known as the category theoretic moment method. This is a relatively new technique as these things go. And the general principle is going to be an extension of the moment method, as the name suggests. Now, as I mentioned, I am a probabilist, and in classical probability theory, the moment method refers to a technique which we apply when we want to study the limiting distribution, for instance, of a sequence of random variables, scalar valued now. And what we do is that we simply compute their moments, so the expected value of x to the n, and you take the limit along the sequence. And if you can understand what the limiting moments behave like, well, then often you can also say a lot about the limiting distribution, provided some mild conditions which are often satisfied. Well, the category theoretic moments method is going to be an extension of this, but now not for scalar valued random variables, but rather for abstract algebraic objects, like the Cokernel. Specifically, the appropriate extension of moments is going to be given by, well, category theoretic moments. And I will define this in some generality, because I will need some more generality than just groups. In particular, in the category of groups, the moment would be the number of surjective group morphisms to some fixed group. But I will define it in the category of modules. So let us fix a ring and a deterministic R module n. Then the n moment of a random R module, say y, is going to be the expected number of surjective morphisms from y to n. So if you like, you can here think about n as being an index similar to the power which occurs in classical moments. And what we'll be interested in is to prove that these moments have nice behavior. And the key thing is that, well, one, that's going to be sufficient to study that. And second, that's going to be easier than studying the distribution directly. Specifically, what I will rely on is a general purpose theorem due to Sawin and Wood, which is relatively recent, which makes that precise. So this general theorem states that if you want to show that a sequence of random R modules converges in distribution, then under certain conditions, it is sufficient to show that the associated moments converge for every fixed R module n. Let me also pause here because I know this is maybe not a technique everyone is familiar with, probably not. So, is this still clear? All right, I see at least one yes, not. All right, and so that is then what I also did. So the computation which one has to do now is to compute the moments of the cokernel. And I here define this in a module theoretic sense, because it turns out that it's quite difficult to compute the moments as an abelian group. This is essentially because, the entries of the cokernel are rather twisted up. You have all these powers of x, and, the independence assumptions which one has made regarding x are not easy to exploit once they are, at the nth power. But what will be easier is to study module theoretic moments, because the cokernel is actually also canonically equipped with the structure of a ZX module. So to make that a bit more explicit, recall that the cokernel is the quotient of Zn modulo the image of W, and W is all monomials of X applied to the all ones vector. So the image, in fact, just all polynomials in X applied to the all ones vector, which is indeed a ZX module when one uses the X structure induced by the matrix X, which we start with. And so, okay, this is a ZX module, and the key trick is to compute the moments in the category of ZX modules. As you see that there is a minor typo on my slide, so I will show that in the limit, this equality holds, not deterministically, not for a fixed index. So as n tends to infinity, the moment converges to that. Okay. Now, at a large scale, the idea will be as follows. We want to study these as ZX module morphisms, especially the number of surjective ZX module morphisms to some fixed module n. Well, if I start with a group morphism, then to descend to a ZX module morphism, well, it has to commute with the action of X. It has to be compatible with the structure of X, of course. And moreover, I can pull it back to Zn if and only if it also kills the all one vector. So, as a consequence, the number of surjective morphisms in the category of ZX modules from the cokernel to this fixed module n, we can also rewrite that as the sum over all surjective morphisms going from Zn to n, which kill one and which behave well with respect to the X structure. So that gives the following decomposition for the expectation. The expected number is the sum with the probabilities that this commutation in fact holds. All right, and then you want to analyze this. Well, the number of summons here is not too difficult to understand. Well, the number of surjective morphisms is basically the same as the number of homomorphisms. And then we have the constraint that we need to kill the all ones vector. Well, that's going to decrease, the number by one factor corresponding to the size of n. So you have the size of this fixed ZX module n to the power n minus 1 summons. On the other hand, for a typical summoned f, one can also see that the probability that fx is equal to fxf, that this should be of the order of the size of n to the power minus n. And the reason for this is also not too difficult to understand. You just simply can look at each basis vector. So for each basis vector of Zn, this commutation relation has to hold. So that gives you n independent constraints. Each of these will decrease the probability by one factor, so you get a power n. So at the very large scale, this is why the limiting moments, which I get ultimately, are the size of n to the minus 1. So 1 over the size of n. I will note that this is really only a sketch, because in particular, this final step here is a bit more delicate. So it's here important that I stress that this is for typical f. In the proof, one has to make a subdivision. So you have to look at specific f, which are, say, very surjective. Then you can make this rigorous. And then you have to look at some f which are a bit less surjective. But then the number of those is less big. So you get some trade-off between the quality of the bounds, which you can establish, and on the other hand, the combinatorics of the number of summons. But nonetheless, the leading contribution is what I have presented here. And then you have some other contributions which you simply have to manage separately. All right. So that is, I think, everything I wanted to present. Thank you for listening to me. And I may note, so as I mentioned, I'm a final year PhD student. So feel free to contact me, in particular if you have postdoc offers.
Okay, thank you very much for the nice talk, Alexander. So are there any questions? I have a question. How does your method or the category theoretic method relates to the proof that almost all graphs are controllable, for example? In this case I see that in this case there is this arithmetic condition, but in almost all graphs are controllable. The rank of the walk matrix it's full, right? So,
Yes, yeah, that's indeed a somewhat related result. I would not say that these results are necessarily strongly related.
ah,
So, I mean, of course, there is to some extent a relation. Also, the same type of people study this, but I think so. The results which you mentioned, so that almost all graphs are controllable.
mhm.
Um, there, one relies on some Littlewood offer theory, and well, it's somehow fairly different.
Ah,
This is to some extent relevant, I think. There are some closer relations. What I
mm,
presented here is for a fixed prime, or at least a finite collection of primes.
yes. Mhm,
Um, but if one also wants to study large primes,
mhm,
so when you allow the size of the prime to depend on n,
mhm.
then well, then you need different type of considerations to actually say that the co-kernel typically will not exist there. So the map will be surjective modulo p.
Okay.
And that is more closely related. So there also one uses Littlewood offer type results, and well,
Mhm,
and that's also relevant to this problem. It's just not something I've pursued yet. So I have studied a fixed collection of primes, but one also has to study large primes actually to fully resolve that conjecture.
mhm.
But that's way down the road at the
Ah,
moment.
in particular for p equals 2,
Mhm.
the condition in Wang's theorem, does it hold for almost all graphs that the rank of the walk matrix modulo 2 or 4 is always full rank? And,
So that is an excellent question. So that this is actually another challenge which I did not comment too much on. So I
mhm,
mentioned my results are not in this setting.
mhm.
And one of the simplifications which it actually gives me is that the prime 2 is much more well behaved.
Ah, okay.
Because in their setting, you will note that this criterion here has different behavior for the prime 2 as for odd primes.
Mhm.
And this is necessary in their setting because the prime 2 has a very peculiar behavior in some respects, which at the moment I have not fully understood why that is the case.
Mhm.
Um, but in the case of directed graphs, or well, well, in different distributions, so if you're not looking at simple graphs, then actually the prime 2 behaves a lot more similar to the odd primes. You can treat them at the same time.
Mhm.
Um, Maybe also to comment on what you specifically asked, does this always hold? I don't think so. So I think it's also with some probability that this condition holds. I don't think
Ah,
it's well, probability different from one.
okay. Not for almost all. Okay. Thank you.